Aristotle said, "The chief forms of beauty are order, symmetry, and definiteness." Have you ever wondered why we are so attuned to symmetry, or why beauty and symmetry are related? The short answer is that symmetry affects function. And here, we will talk about a method for codifying symmetry called group theory. Group theory is an area of math with an extensive history, and mathematicians haven't limited themselves to 3 dimensions. One of the groups they've discovered is simply called the monster, with 196,883 dimensions. If you would like to hear more about the monster, please head over to one of our favorite channels, 3 Blue, 1 Brown, and see his video. For most applications, that number of dimensions is a bit excessive, but we can do a lot with groups that stop at 3 dimensions. This video will give us a basis that will be used to solve many different problems in chemistry, but first we need to build up a language in math around symmetry of 3-dimensional objects. Symmetry often determines function in many aspects of life. Sphere-like viruses have been found to have protein shells called capsids with icosahedral symmetry that are made of various proteins that fit together to form the shape. One example of this is the cowpea chlorotic mottle virus, or CCMV. Researchers have shown that if you take its capsid proteins in vitro, they self-assemble into this icosahedral sphere. Here you can see the 5 and 6 membered rings put together in a soccer ball-like shape. It's not just tiny things that are dependent upon symmetry for their function, of course. Cars, for example, have a plane of symmetry that runs vertically from front to back that's required for their function. If they were very different on the left and right side, say the tires were much larger on one side than the other, they would easily roll over going around a corner. As humans, we recognize symmetry and find more symmetrical things in general to be more beautiful. There are websites that you can use to measure how symmetrical your features are and compare with others. I did it so you don't have to. To get some frame of reference, I put in the pictures for Ryan Reynolds and Brad Pitt that were on Wikipedia. As you would probably expect, they score well into the 90% range on facial symmetry. Then I uploaded a screenshot that I use on my online meeting software that just came from a screenshot during a meeting. It said that I'm 77.3% symmetric. I guess I have a face suited for chemistry. In fact, I'm in the ballpark to go looking for the one ring, apparently. Then I was wondering how consistent it was, so I took a new shot of myself from my computer camera while I was writing this. Seems a bit inconsistent, but definitely still not leading man material. All I probably learned is that I should change my picture I have on Zoom. Having a mathematical way of quantifying symmetry can tell you a lot about molecules as well. We will use symmetry to determine the vibrations in a system. We can also use it to understand their electronic structure and the number of different wavelengths of light they will absorb. This can result in a greater understanding of everything from reactivity to photovoltaics. Before we can discuss applications, there's some fun to be had in just playing with symmetry and learning how to quantify it. To illustrate and play with in this section, let's use an interesting little molecule called squaric acid dianion. So this is squaric acid, probably named for obvious reasons. Double deprotonation gives a very symmetrical compound with extensive resonance. Resonance is a familiar topic to most folks, at least in compounds like benzene, but it can happen in lots of compounds in lots of different ways. It's simply where many different ways of drawing a molecule can contribute to what's called a composite structure, which is basically the real electronic structure to the extent that chemists can agree that there is such a thing as a real electronic structure. The structures that contribute to the composite structure are called resonance forms, and the double-headed arrows are reserved in chemistry to show these different electronic contributions. In this case, all the resonance forms contribute equally, but that isn't always true. The composite is an average of all the resonance forms that contribute, so the composite structure for squaric acid dianion has a 0.5 minus charge on each oxygen, 1.5 bonds between each carbon and oxygen, and a 1.25 bond between each pair of carbons. Basically, for our purposes here, all you really need to know is this compound is symmetric with all the CC and CO bonds equal. To better see what happens when we move the molecule around, we will sometimes add artificial labels to make the atoms different, like this. Squaric acid dianion is a good choice as an example because it is a very simple molecule that has all the symmetry operations we will be discussing, although there are plenty of other choices with the same property. Perhaps the first thing to define is invariance, which just means not changing. When we do a symmetry operation, the object of interest should be invariant to the operation. This doesn't necessarily mean we didn't do something, although it could mean that. More generally, if you looked away, we did the operation, then you look back, you wouldn't have any way of knowing that anything happened. So if we have a triangle and we show you a 120-degree rotation, you could argue something happened, especially if we include the artificial labels that have rotated. But it looks exactly the same without the labels. We say a triangle is invariant to a 120-degree rotation. We might also say that the triangle has a rotational operation of 120 degrees. It's a property of the triangle. Next, we need to define a symmetry operation. A symmetry operation is an action of some kind that leaves the object invariant, like the 120-degree rotation of a triangle we just discussed. All of that is easy enough, but we need to define these things and give a shorthand for them. There are 5 kinds of symmetry operations, and in some cases there will be subcategories. All the symmetry elements will run through a single point in the middle of the object. As a result, we will have what are called point symmetries. There are other kinds of symmetries where we bring in translations like space groups used to understand the structures of crystals, but we'll leave those for another time. The first point group operation is identity, which is given the symbol uppercase E. For this one, you can think of it as doing nothing or rotating an object 360 degrees. Every object will necessarily have this operation. Identity is here for mathematical completeness, but believe it or not, it will have some mathematical utility when we start to look at applications of group theory. The second operation is a proper rotation, which has the symbol capital C sub n. This is rotation around an axis in the middle of the object. The n is for 360 degrees over n, the minimum number of degrees rotation required to make the object invariant. For a triangle, this was 120 degrees, which we call a C3 rotation. For a square, it is 90 degrees, which would be a C4 rotation, and so on. Here, we will use the convention that a positive turn is in the clockwise direction and a counterclockwise turn is in the negative direction. For proper rotations, sometimes we can do them more than once to get a different configuration according to our artificial labels. For a C4 done twice, C24, it would look like this, which is the same as a C2, a half turn. A C3-4 is a 3/4 turn. It is also a C-1-4 turn, a quarter turn counterclockwise. If you do any proper rotation n times, you end up back where you started, so it is equivalent to identity, capital E. The third operation is a mirror plane, or better, a plane of symmetry, which is symbolized by the Greek letter sigma. Basically, this is a plane running through the main point, on either side of which things are identical. People have an approximate vertical plane of symmetry. Our squaric acid dianion, for example, has 3 different planes of symmetry which are given different names. At this point, it is convenient to define what we will call the principal rotation axis. Defining a set of axes for any problem you're working on in group theory is an essential step, and the convention is to use the highest order rotation axis as the z-axis. For squaric acid dianion, it is the C4 we just talked about. Then, the CO bonds in this compound make a natural choice for the x and y axes. The first kind of plane of symmetry is coincident with the highest order rotation axis. It is the plane that runs through the diagonal corners of the square, and there are 2 of them. These are called vertical mirror planes, given the symbol sigma sub v. There's another kind of vertical plane of symmetry, which you may have noticed. These are planes running between the carbons. Again, there are 2 of them. These vertical planes are called dihedral planes of symmetry and are given the symbol sigma sub d. Finally, there is a third mirror plane. This one is perpendicular to the z-axis and splits all the atoms of the molecule in half. Since it is perpendicular to the z-axis, it is called a horizontal mirror plane, with the symbol sigma sub h. The fourth operation is an inversion center, or point of inversion, given the symbol I. If this operation is present, the point xyz is identical to the point negative x, negative y, negative z. Looking at familiar planar shapes for a moment, the ones with even numbers of sides, squares, hexagons, etc., will have an inversion center. The odd ones do not. This will carry into 3 dimensions as well, where we call things with an inversion center gerade, German for even, and things without an inversion center ungerade. For our example, the inversion center is in the very center of the square. Inversion will convert carbon 1 to carbon 3, and so on. In the end, inversion ends up changing our labels just as a C2 does for this particular molecule. That is not always true for these different symmetry operations. Finally, we have the improper rotation with the symbol capital S sub n. An improper rotation is perhaps one of the harder symmetry elements for some to see. It is a single operation that we can think of as occurring in 2 steps, a proper rotation and a mirror plane perpendicular to that rotation. An example of a familiar molecule with an improper axis is methane, which we'll inscribe in a cube. If we follow H1, we can do a quarter turn, a C4, then reflect perpendicular to that rotation, which will move H1 to the position of H2. It also interconverts all the other hydrogens. Methane is an example of a molecule with an S4 that does not also have a C4, so the proper and improper rotations are independent of one another. In the case of squaric acid dianion, the S4 is coincident with the C4, and the operations do more or less the same thing. The molecule is flat, so the perpendicular plane of symmetry doesn't do much. Improper axes are usually only listed for n equals 3 and higher. An S1 axis is the same as a mirror plane, and an S2 axis is the same as an inversion center. Your intuition is probably telling you that not all molecules have the same symmetry, and we can group together molecules that have all the same symmetry operations. It turns out there are a finite number of ways of combining symmetry operations into groups. Mathematicians have a very precise definition for what constitutes a group, which we don't have to go into here, except to say that it has everything in it that it can possibly have in it, no more or less. So as we describe the symmetry operations that are in a point group, you don't need to wonder what would happen if we took this operation away or added a different one. The answer is either that gives you a different point group, or the thing you're adding is already described by something else that is in the group. A point group is a complete and closed set of operations. Some very different looking things can be in the same point group. For example, both C60 and B12H12 2- are icosahedral and are in the point group IH. Similarly, BF3 and PCl5 are in the point group D3H. Our example squaric acid dianion is in the same point group as platinum tetrachloride 2- and axially distorted copper hexachloride 4-. We can define all the point groups that molecules usually fall into and write down what their symmetry operations are. These can be found in what are called character tables. Searching the term on the internet or looking in an inorganic text will bring them up for you. Personally, I like the website we'll put in the show notes, which has a lot of useful tools. Here's an example for the point group called D4H, which is called Schoenflies notation after mathematician Arthur Schoenflies. The symbol D4H uniquely identifies a collection of symmetry operations that form a group. The columns are organized into classes of symmetry operations. Again, there's a formal definition for what operations are in the same class, but for our purposes, they are simply operations that behave similarly. D4H has a C4 with 2 members in the class, which are C14 and C34. The C24 equals C2 is in a class by itself. Some operations are always in a class by themselves, like inversion. Where the D4H symbol comes from will become obvious with a few examples of assigning point groups. But the D indicates that there are C2 axes perpendicular to the principal rotation axis. This is pretty common in high symmetry objects like our squaric acid dianion. The 4 means there is a C4 axis, and the H means there is a sigma H plane of symmetry. One way to assign a molecule to a point group would be to look at all the symmetry operations and then just look in the character tables, which would be tedious for some molecules with lots of operations. As you might guess from the symbols, if you look at a few symmetry operations, you tend to find all the other ones as well. So for squaric acid dianion, The symbol D4H only indicates that there's a C4 with a perpendicular mirror plane of symmetry, indicated by the H, the perpendicular C2 axes, indicated by the D. Having some symmetry operations requires other symmetry operations to be present, so we can simplify the label down to a few operations. As a result, we can create a flowchart to follow that will help us to assign point groups like this one, where we just find the essential symmetry elements that generate all the other symmetry elements. Here's a few examples where we'll use this flowchart to find the point group for molecules. Basically, it's an exercise in symmetry where you try to rotate the molecule in your mind to find the different operations. It's a game you can play with any three-dimensional object, not just molecules. Let's start with an easy one, dinitrogen, which is about 70% of the air we breathe. We start at the top of the flowchart. Is it linear? Yes. Linear molecules have a C infinity axis, meaning they are the same no matter what increment you rotate them along one axis. The next question in this branch is, are there C2 axes perpendicular to the C infinity axis? In this case, there are, so our molecule is D infinity H. How about water with its bent structure? Is it linear? No. Low symmetry? In this context, low symmetry means that it has no Cn axis of any kind except for the C1 that everything has, so no. The next box says, find the highest Cn axis, which is a C2. Are there non-coincident Cn axes higher than n equals 2? These are for very high symmetry groups, which we'll do some examples for later on. The answer here is no for water. The next box asks if there are perpendicular C2 axes. The answer is no. That puts us into a C or S group, and the S groups are not common. The next box says, is there a sigma H? A sigma H would have to be perpendicular to the C2, so the answer is no. If we try to do this mirror plane, we could easily see that the molecule is moved, so it is not invariant to a sigma H. The next box asks if there's a sigma V. There are in fact two of them, but we really only need to notice one. Water is in the C2V point group. Here is the whole C2V character table, like you might find it in various resources. The whole character table will be useful for a variety of different applications, but here we're really just dealing with the Schoenflies symbol, which we just found, and the symmetry operations on the first row. All of the symmetry operations are listed, and in this case, there's only one operation in each class. How about something a little more complicated like PCl5, which has a trigonal bipyramidal structure? The compound isn't linear. It isn't low symmetry. It does have a rotation axis. The highest order rotation axis is C3. It does not have other non-coincident axes that are C3 or higher, so it's not in a high symmetry group. It does have perpendicular C2 axes. This puts us into a D group. The next box asks if the molecule has a sigma H, which would be a plane of symmetry perpendicular to the principal rotation axis, the C3. The molecule does have a sigma H, so it's in point group D3H. The character table shows all the symmetry operations. Every point group has identity listed first. Next, there are two C3s, a C13 and a C23. The three C2 axes perpendicular to the C3 are in the next column. The sigma H is next. There are two improper rotations, S13 and S23, coincident with the C3 axis, but not identical as they interconvert the atoms on the axis. Finally, there are three vertical mirror planes that contain the principal rotation axis. Let's finish with a couple of very important point groups. Let's assign methane. Quoting myself from earlier, the convention is to use the highest order rotation axis as the z-axis. Note that it is the highest order rotation axis that is chosen to be z. The principal rotation axis can be either a proper or improper rotation, whichever one has a higher order. In methane, the highest order proper rotation axis is C3, but the highest order improper rotation axis is in S4, as discussed earlier. So we can make the S4 the z-axis, which is between the carbon-hydrogen bonds. The x and y axes are also between the bonds, but in the same planes as the HCH wedges. Going through the flowchart, the compound is neither linear nor low symmetry. It has C3 axes, and it has C3 axes that are non-coincident, which puts it into the high symmetry category. The high symmetry groups have 3 branches, separated by the nature of the highest order proper rotation axis, which is 3 here. So we're in some kind of T group. If there are no planes of symmetry, then we're on a pure rotational group, T. But we definitely have planes of symmetry in methane. Those planes of symmetry contain the C3 axes. In other words, they are vertical planes. So this is a TD molecule. Molecules that we think of as being tetrahedral, like methane and TiCl4, are in TD, which is a relatively simple high symmetry group. It only has 5 classes, although the number of operations in the group, which is called the order of the group, is a relatively high 24. That's twice as many symmetry operations as in the D3H molecule we just discussed. As always, there is identity with the symbol capital E. Then there are 8 C3 axes. The C3 axes are along each HC bond, which gives you 4. The other 4 C3s are C23, or equivalently C-1,3, where you rotate counterclockwise instead of clockwise. The C2 axes bisect the HCH bonds and are coincident with the S4 axes. There are only 3 C2 axes because rotating a C2 the opposite direction isn't a new operation. However, there are 6 S4 axes because the S34 operation is different from the S14. Then there are 6 mirror planes. That there are mirror planes is obvious, but it can be a little difficult to identify the unique ones. Think of it this way. You can have any 2 CH bonds in the plane of symmetry, and the other 2 will be split by the plane. As an example, here is H1CH2 in a plane, and H3CH4 out of plane. It turns out, if you have a group of 4 things, there are 3 ways to organize them into 2 pairs. If 1 and 2 are in the plane, then necessarily 3 and 4 are out of plane. Here are all the 3 ways to organize them. But then, you need to swap the ones out of plane with the ones in plane. This gives you 6 unique planes listed in the character table. Those are all the symmetry operations in a tetrahedral system. The final system we will look at in this video is the 6-coordinate complex cobalt hexachloride 3-. This compound has all the bond distances the same with 90-degree and 180-degree bond angles, so you'll probably recognize it as being octahedral, which has a symbol OH. From a flowchart, this means that it has multiple C4 axes, along with planes of symmetry and an inversion center. The character table for OH can be a little intimidating, but here it is. Let's pare it down to just the symmetry operations. The order for OH is 48, so there are a lot of symmetry operations. We'll point out one member of each class, but you are welcome to try and find them all. It's worth pointing out that OH is an exception to our rule. At least in most cases, we use the highest order rotation axis as Z. The highest order rotation axis is an S6 between the chloride ligands, but usually we use the C4 as the principal rotation axis. The reason for this in this special case is that every ligand is on the Cartesian axis if we use the C4, which makes it very convenient. There are some circumstances where using the S6, which is between the ligands, as the Z-axis is convenient, but most of the time it's nice to have all the ligands on the axes. The first operation after identity is C3. Maybe it's a little easier to see some of these operations by looking at the solid octahedron rather than the molecule with all of its symbols. An octahedron has trigonal faces, and 2 of these on opposite sides of the molecule are traced. Through the center of these faces is a C3 axis that is one of the ones listed. There are 4 such faces on top and bottom of the octahedron, which contain the axes for 4 C13 and 4 C23 operations, the 8 shown in the character table. Next, C2 is listed, and these C2s are the ones that run between each Cl, CO, Cl angle. The C4s are perhaps the easiest operation to see in the molecule. Next, the character table has C2s that are equal to C24s. So these are the C2s that are along the bond axes, and there are 3 unique axes. An octahedron is a Gerada system that contains an inversion center. There are 6 S4 axes that are coincident with the C4 axes. The molecule remains invariant to the plane of symmetry done after the C4. The S6 axes are coincident with the C3s in the middle of the faces of the octahedron. There are sigma H's, perpendicular planes of symmetry to the C4s. These are 4 chlorines in each plane. Then there are vertical planes that have the cobalt and 2 chlorides. These are labeled as dihedral planes because they run between the axes. Assigning point groups and finding symmetry operations turns out to be way more useful than I probably let on in this video. Here we were mostly just looking at symmetry operations and how they add up to point groups. However, we can use this as a basis to discover very fundamental and useful things about systems that have some type of symmetry. And I'm looking forward to other videos where we will be able to describe those in more detail. If you enjoyed this video and want to support future videos covering topics like this one, please subscribe to our channel and give us a thumbs up. We make these videos for fun and as a way of interacting with and giving back to the community, so we greatly appreciate your support.